we have a couple of cells in series. We can have as many as we want, and especially in industrial application, you can have, you might have a line of 20 or 30 that are all lined up, but we're interested in less than that. So in a way, it's sort of a bit of deja vu, if you like. These are looking a bit like, these look a bit like electrochemical cells, don't they? But they're not. Because what we're doing is we are pumping in electrons. Remember, this is the positive side and this is the negative side. This would mean in electrolysis, what electrode is that? Anode. And what charge does it have on it? Positive. This electrode?
Cathode.
And it's negative. Yep. And so if our electrons are flowing that way, away from the negative terminal, then they need to keep going in a big loop. So they're going through here, all the way back to our first cell. We can have any metal ion in each of them. So this way we're using our current with our electrons moving through our cells to reduce 3 different metals in 3 different cells at the same time. Now the thing that they all have in common is what? The current. The current is the same for all of them. What's the current? Remember what the current is.
The rate at which the charge moves.
The rate at which the charge moves. That's exactly right. Now, that rate is the same because if we think about what is involved in the movement of electrons, then they're being repelled from like charge, the negative terminal, and they're attracted towards the positive terminal. But they're all moving at the same rate through the system. So we can't have one electron zip through faster than the others. It's like a river. If you put a stick in and you watch the rate at which that stick flows through, it's flowing at the same rate as all of the rest of the river is. So that's the same thing for our electrons. Now, in our example, we were actually given 2 electrolytic cells, and we're told that in cell 1 we have 0.785 grams of silver reduced from a silver nitrate solution using carbon electrodes. So in all, we can say that these ones are carbon as well. It doesn't really matter. Determine the mass of the chromium metal. That is reduced in the other cell if carbon electrodes are used. Now, the information we've been given is a mass. So what are we going to need to do as our first step? Moles. So if n equals little m on big M, or the sample mass divided by the atomic mass in this case. That's how many moles we have. Now, in this case, we're just asked about chromium. We haven't been told anything about oxidation number, so where are we going to look to find the information about the ECS? What's on the ECS for chromium? The reduction half equation. What does it look like? Cr3+. So we know we have this many moles of silver. If we were doing this for any metal, what's something else that we're going to need to do? Or something we need to look at?
Get the moles of electrons,
We want the mole of electrons, yeah. Well,
which you've got, it's just the same.
yeah, we need the reduction half equation for this one, don't we? So we can work out that moles of electrons. Now, as it happens, it's pretty straightforward in this case, but we should always look at that to make sure that we know the moles of electrons, because we've already established that the current's constant. These, doesn't matter how many cells we have, they're all going to see the same rate of appearance of our electrons. So what does this tell us for our moles of electrons then? Yeah, so our moles of electrons is the same. Okay, now again, this is the spot where students get confused which way around to, what to do to those moles of electrons. So this is the moles of electrons that we have. What do I need to do to this number to work out the moles of chromium that I'm going to be reducing? Divide by 3. Does everyone agree we're dividing by 3? Yeah, because, and it makes sense. If we look, this one's got a 1 that we don't bother writing. It's got to be less than this one. This one needs 3 electrons, so it needs, for every atom, needs 3 electrons. And so we're going to divide by 3. Or multiply by a third, it's the same thing. 0.002423 moles. And this, like I said, this step here is the one where most errors occur. So spend a minute thinking about whether you got that ratio around the right way if you think you got yourself a little bit confused. And our last step to find the mass is then the moles multiplied by the atomic mass of chromium gives us 0.126 grams. And we could go on and do it for a third cell. Okay, it wouldn't matter how many there were, because we already know the moles of electrons. As long as we know which ions we're dealing with, or we could also be asked what's happening at the cathode, at the anode as well. We could be asked about oxidation reaction quantities as well. But once we know this, we can work out everything for all of our cells connected in series. Everyone's sort of looking around, sort of